For the last part of this lecture today, we're going to look at a little bit of added stuff that's not something I'm going to test you on, but it's pretty fun stuff, and it shows you where some of this calculus can lead to just other branches of mathematics that you just wouldn't expect necessarily. We saw a little taste of it in the last video. I'm looking at the Newton's method file that's on my website. I've changed the function here to a fifth degree polynomial just to give it a little more flair here. Fifth degree polynomials in general will have 5 x-intercepts. So by solving that equation there, we'd be looking for these intercepts. This is not easy to do algebraically. Sometimes it can be done, but sometimes it's just nigh on impossible to do it algebraically. So we have these methods, like Newton's method, to do it um, numerically. So we can take different, um, like we did before, we start with a different input value. If I want to say find this intercept here just a little shy of 2, I might take a guess of 2, and it'll zoom in on that intercept there. It looks to me like this fifth degree polynomial actually has only 3 real x-intercepts, and there's apparently 2 complex ones. This right here, where the fifth degree polynomial bends almost like it's going to start going back up again, then comes back down again. Those are the 2 missing x-intercepts somewhere in that area. I see just 3 of them here. One down in the negatives, and one a little less than 1, a little bigger than 1. So yeah, the bigger than 1 is here with 1.66. I can get the smaller one. Let's take an initial guess of 1 and see if that'll go down to the smaller one here. So I'm going to stick a 1 right there. Yeah, there we go, 0.74. All right. So 1.66, 0.74, and then the last one, let's guess -2 here. And let it zoom in on there, negative 1.78. So we've got 2 positive x-intercepts and 1 negative. What I want to look at, though, is I want to look at it back on this complex graph down below. So I'm scrolling down. And this is substantially more complicated than what we saw before. Now I got a fifth degree polynomial, so I'm expecting 5 x-intercepts. I can see the 3 real ones. Here's the light yellow, which would be the one that's just a little bigger than 1. Here's a darker yellow. That would be the one just less than 1. And here's a shade of blue, which is the one that's the negative, what was about 1.7. Okay. And then these 2 are the other 2 x-intercepts, those 2 colors, complex numbers. The again, this graph here is showing for each value, so each location in this graph is a particular number, either real or complex. The real is straight through the middle here. Everything else has some imaginary piece to it. The color that appears at any point is the result of Newton's method. Actually, I have this 25 iterations right now. So if I start with this point right over here, and I iterate with that being x0 25 times, I'm going to be getting very close to that x-intercept at 1 point, whatever it was, 1.6, I think. Right. With a starting point over here, I'm going to be getting close to that negative x-intercept. Starting point up there, be a complex starting point. We really don't deal with those yet, but anyway, would be converging to one of those complex roots. Now, I want to zoom in a little bit. There's some interesting things that are happening in between these regions. So I'm going to zoom in here and see. It looks kind of blocky because I don't have the resolution up very high because it takes longer to calculate. If I click this button right here, it'll increase the grid density to make a smoother picture, but it takes 4 times as long to draw. So I get the the pleasure of sitting here talking to you while it's calculating. I'm being told to stand by. I am actually sitting by. And you can see the different, these are called basins of attraction. That is, each one of those 5 x-intercepts attracts other starting points to it. So you start with x0 equals something, and you start iterating, and your outputs get closer and closer to one of these intercepts. 3 real ones. Again, there's that light blue, there's the light yellow, and the dark yellow. That is, along the real axis, you will only see those colors. But as soon as you get off the real axis, you start seeing some other of the colors. Let's try zooming in off the real axis down into something. Oh, I don't know. I'm just guessing what might be an interesting region. But the thing is, this is chaos. This is a fractal. It's generated by just simply taking a starting point and looking what happens. That as you iterate through Newton's method from some particular x0, you see what the various outputs are. And each output gets closer and closer to one of the 5 x-intercepts. I then color the point in the plane that I started with by the color of the output after 25 iterations. And you can start to see some interesting designs here. Almost looks like an elephant trunk here, but the elephant trunk is made up of a whole bunch of little elephant trunks. Let me zoom in on one of these little elephant trunks here. It's just fascinating to me to see all these different patterns that come out of this simple Newton's method algorithm. Uh, and this is very common when you're dealing with fractal design and fractal creation. You have a reasonably simple um, set of rules that you just do. You take your output and you plug it back in and you do it again, and you take your output and do it again, and you look at the results. And the thing is, with chaotic dynamics, there's a sensitive dependence on initial conditions. That is, if you move over just a little bit, it could be that your result is vastly different than where you were when you started. So you see points very close together. I mean, you look at the decimal difference between here and here, we're talking, 0.005 moving from here to here. So we're dealing in the 3rd decimal place here, and yet we've got this whole intricate um, collection of different places where um, the sequence that you get out of Newton's method converges. I'm going to zoom in again on something. That's oh, it looks interesting. Let's look at this point here. And again, each time it's taking each point in the complex plane and the rectangle that I selected, using that as an x0, iterating it through Newton's method, that is calculating x1, x2, x3, all the way up to x25. Then it looks and sees what the result is, and you can see that points very close together are getting different results because they're being colored different colors. And there's all sorts of different patterns that we see. I can still see um, the 5 x-intercepts in the 5 different colors here, the light yellow, the dark yellow are the 2 positive reals. This shade of blue is the negative real, and then these 2 are the complex roots. Anyway, this is a brief introduction to some fractal design and chaos theory that you just run into unexpectedly when you start doing these types of iterative numerical processes. Newton's method works great when it works. It converges fast. When it doesn't converge, I wouldn't say it doesn't work. It just works at doing something else. It works at generating these fantastic fractals. Anyway, we will see you all on Friday.